Okay, so you should watch the video of me going over this page before you watch this video, just to make sure that you're good um, on how to read it, how to read the pedigrees, and how to um, understand like what the lines are and all that kind of stuff. Just for the record, and it also goes over the dominant, recessive, autosomal, sex linked again, just to make sure that you're good with that. Um, so here I wanted to give you some hints so that you can finish this pedigree practice on this page here. So again, autosomal, remember, means automatically have two of each. So if you see autosomal, what that means is it's not sex linked. So we just use our regular letters the way we normally would, with like big A, big A, big A, little a, whatever. But in this case, it is a dominant disease. And don't let that freak you out. It is the same thing as talking about like brown eyes are dominant. So if someone has a big A, that means they have brown eyes. Or in this case, if they have a big A, that means they have the disease. Okay, so it's the same exact thing. Um, but in this case here, a lot of times, if it's a dominant disease, that means it's pretty bad, because that means if you get one copy, it messes you up completely. So usually two copies of it, that big A is going to be fatal. In particular, I know for a fact that achondroplasia with dwarfism, if you get two copies of that, then it's fatal, because achondroplasia dwarfism, remember, that's where you have a normal sized torso, but you have short, long bones. So like your arms and your legs and stuff like that are not the length they need to be, because there was an issue with the growth of those. And those kinds of bones are really important because they have a lot of the bone marrow that make your blood cells and stuff like that. So if you have two bad copies of that allele, then generally you're not going to be able to survive, because you're just not going to be able to make the stuff you need to make from your bone marrow that comes from those really, really important long bones. So in that case, big A, little a generally is what someone is if they have the disease, and little a means they don't have it, because remember, little a does not have a big A. In this case, the disease is dominant. Okay, so if it's little a, they don't have the dominant allele, which means they don't have the dominant trait, which is the disease. So also, so when we look at the pedigree here, remember that if it's not colored in, that means that it does not have the disease. If it's square, that means it's male. Circle means it's female. And if it's colored in, that means it does have the disease. So in this case, anybody who's not colored in means they do not have the disease. And if the disease is dominant and they don't have it, that means they don't have the dominant allele. So everyone who's not colored in is going to be little a, little a. Whereas everyone who is colored in has got to have at least one big A. But here's the hint. We know that everybody who's in this pedigree here actually only has one big A. Because if this mom here was big A, then all she would be able to give would be a big A. And her daughter doesn't have it. So she had to be able to give her a little A. And same thing with this guy right here. Or this guy right here, so his dad had to give him a little a, so he has to be heterozygous also. And then this girl right here, her mom had to give her a little a. So when it's asking the genotypes over here, it's asking you to tell me whether they're big A, little a, or little a, basically, because big A does not exist in this particular pedigree. And the numbers here mean what generation they're in, and then it just counts over. That doesn't mean that there's 4 offspring in this row here. That just means that that's the 4 people that are in that generation. There's actually only 2 offspring right here. So that gives you that answer there. And when you're talking about how things are related, you're looking at how they're connected. So for example, the 2-2 and 2-3 both have the same parent, so that's a sister and a brother. Okay, so for autosomal recessive, so remember, autosomal in both of these cases means it's not sex linked, and if it's not sex linked, you're just going to do it normally, just with the big A, little a, whatever. But in this case, the disease is carried on the recessive allele. So thankfully here, since the disease is recessive, that means that not having the disease is dominant. So if you're big A, little a, you're good. You're in the clear because you have a big A. The disease is recessive. The big A covers the disease, and you're good. So you don't have the disease. However, you can pass it on, which means that you are a carrier if you're heterozygous. So this pedigree right here, it shows you that this dad did not have it, but the mom did. Her daughter was not affected, but her daughter's son. So her grandson, ooh, that's a girl. Her her granddaughter has the disease, which means that her daughter had to pass on that little A. Even though she did have a big A, so she was not affected. So she had to have a little A because she got it from her mom, but also we know she had to have a little A because she had to be able to give it to her daughter. That means that her dad also had that. That means that little girl's dad also had the little A. But remember that generally, if someone's coming in from outside the family, unless we have evidence that they have the disease, then we're going to assume they don't. But in this case, it gives you evidence that he does have it, or have the allele. And in this pedigree over here, actually, same thing, because we have a couple having a daughter. I just realized I drew almost the exact same pedigree twice. But notice that it skipped that generation, which means it had to have a carrier. Autosomal dominant does not have carriers because it doesn't have someone who it can hide in. Because if they're big A little a, they have the dominant allele. It's a dominant disease. They have the dominant disease. But if it's recessive, then they have the ability to have it be hidden, and that makes them a carrier, and they can pass it on. And because it is autosomal, we're not dealing with X and Y, so everyone just gets 2 A's, which means that it's going to be about equal in males and females because there's not really going to be a difference there. So when we look at this problem down here, think about what these two parents have to be in order to have one kid that does have the disease, and then you're going to do a completely separate Punnett square to figure out a chance of just another child with the disease. Remember that just because this one child has it, that does not affect the chances for any other children. It's a big misconception for just, let's say, like, whether or not you're going to have a boy or a girl. Let's say that we have a couple. I know one of my cousins, he had 3 daughters and no sons. He had 3 daughters and no sons. And so everyone's like, oh, well, he already had 3 girls. That means that the next one has to be a boy or something, which is totally ridiculous because they did have a 4th kid and it was a girl. So every single time the chances kind of reboot. So if there's like a half chance of someone having the recessive trait in any kind of Punnett square from the parents, for example, every single time it's a half chance. So I don't care if they have 18 kids. 18 kids. I don't care if they have 18 kids who have the disease. It's still a half chance next time. Okay, so and remember when you're setting that Punnett square up that you're just going to use the regular A's. You're not using X's and Y's because it is autosomal. For the sex-linked, remember that is where you use the X's and Y's. The X's get a letter put on them and the Y's do not. Because the Y's are tiny little chromosomes that basically carry the genes that are needed to make someone physically a male. So that's pretty much all it has on there. So the Y is not actually an essential chromosome, or else females would not be able to survive. So, but the X actually is an essential chromosome. It has a whole bunch of important stuff on it, which is why it can mess with your blood clotting. Hemophilia is where you are not able to clot your blood normally. Because your platelets are not working, so you can get like a tiny little cut or a tiny bruise, and it just goes way out of proportion because you're not able to stop the bleeding. Male pattern baldness, that's why it's a lot more likely to see males that have the bald head super early because it's going to be sex linked. And then red-green color blindness, where your the receptor in your retina that's responsible for distinguishing between red and green cannot distinguish between it. So it knows it has to be one of the two, but it's not sure which one it is. So when we're looking at the pedigree here, it's more likely for males to have a sex-linked because if they get one copy of the allele here, then they're diseased. Whereas if they get the big allele, then they're good. But they can't be a carrier because they cannot have 2 alleles because they have a Y instead. Whereas females can be carriers. So for females, it works exactly the same way as everything else, but for males, it's different. So for example, so he has a disease, which means he is X little a Y because it's recessive disease. And he's a boy because he's square, which means that he got the Y from his dad and he got the X from his mom. So that means his mom has to be a carrier because he got the Y from his dad. So the only place he could have gotten that X is from mom. And his daughters will always get that X from him because he's not going to give his daughter a Y because then his daughter won't be a daughter. biologically anyway. So, if a male has a disease that's sex linked, it came from mom, not dad. So that's how you can tell here. So, and then a male here, like this dad here, we know that he doesn't have that allele because he doesn't have the disease. There's no chance of him being a carrier because he only gets one allele, so he has to be X big AY. And then for the females, where we're not really sure, I'm not really making you responsible for identifying what those genotypes are, because we're not really sure. It's basically a half chance of them being a carrier or totally unaffected. Um, so that should help you with these questions. If you have any other questions, please ask.